Hi guys, me again. First things first, Happy New Year and all the best wishes. Next thing, what's new for this year? Well, this year I'm starting to upload the StarDrive Finalized series. And in addition, I've started my own company. Hopefully this makes me look a bit more professional. Don't know whether it works, but we'll see. My website, I'll show you. It's a familiar website. I have it for years. It's called VEDODER. And my company is called VEDODER R&D, Research and Development, www.vedoder.eu or com, or even NL, since I live in the Netherlands. Dutch is my native language. What's interesting is StarDrive Dutch, that's what we're talking about now. This is the original StarDrive. It is in Dutch, so it lacks pictures, it lacks YouTube video, so it's not very useful. And it's a bit ancient, it has a few fails in it, and of course I learn as I go, so I would skip that. I would skip the translation either. I would just start out with Revisited, which is uploaded to YouTube and of course to my website, including pictures and full English translation. Now the next edition is the Finalized series, which is the mathematical model behind StarDrive. This is the first upload telling you something about photons. Now, how do I work? How does my company work? What I do first is I protect my papers. Whatever I write or invent or boil up, I protect it. I deposit it as intellectual property. So it's mine, that's it. You can't beat that. And the next thing is I publish it. And this might maybe like a contradiction, but it's not. What I want you, I want me, I want the entire world to be able to work with StarDrive, to work with my findings, to use my findings as a vantage point to even excel or overtake me, I don't care. I want this world as a whole to progress. So that's why I publish it and protect it. I want to make sure that no one else can come along, say I don't protect it, someone else comes along and says, hey, nice theory, you know what I'm going to do? I'm going to copy it and make it my own, and then I'm going to forbid the world, including me, to work with it or to copy it. Well, that's not going to happen. It is mine, it's deposited and of course published. When something is published, you cannot patent it anymore. And the shit is out of the dark. You can't patent it anymore. So that's why I do it. What else? A mathematical model, why? Well, first off, what you need is 3 lengths. If you need a table top to be solid, to be stable, you need 3 supports at least. One support being your general observations. I'm talking about a physical model now. General observations, experiments, outcome of those experiments, that's one leg. And it has to be in full compliance with the model you make, the atom model, and all those interactions. After you boil up, it has to be in full compliance with those experiments and the outcome. Not with the conclusions, because those are, well, they can be wrong conclusions. Scientists who do experiments, they draw their own conclusions. Forget about it. Just only use the outcome of the experiment, because you can't tamper with that. Now, so you have your experiments, your general observations, one thing, and then you got your physical model, your tangible model, physical model, and then a third step, you need mathematics. And when using mathematics, you will find the errors in your work. They just pop out like that. Oh, wait, there you're wrong, there you're wrong. You need to have a sound. If you can't support your atom model with mathematics, it's worthless. You need a sound mathematical model as well. So that's one thing. Other thing which makes it important is when you have mathematical models, you can fine-tune the things. You can fantasize about, say, a hydrogen atom spinning in space and then creating those spectral lines because it hits with gravitons, and then these gravitons fuse and so forth. That's nice, that's interesting for concepts, but it's not precise. You need to have the precise equations of each collision and each spectral line. If you can't support that, forget about it. You need those. So for fine-tuning, mathematics is very important. And the first thing is, most scientists, I've been knocking on doors all my life trying to get some recognition for the things I do. But most scientists see that they think mathematics is the language of science. So you need a mathematical model to begin with, only to be heard. So reason enough to published in the mathematical model. And this is the first chapter, Flight of the Photon, part 2 out of 3. And the thing is, why starting with part 2 out of 3 and not part 1? Part 1 out of 3 is about emitting photons. This is part 2, the flight of the photon. Then you got part 3, receiving object. Now, emitting photons, black body radiation, electrifying things, you get those photons emitted. That's one way to do it. And this means creating photons. At the other side, receiving object, it can be a mirror bouncing it back. It can be anything. It can be a water droplet creating a rainbow. It can be a hydrogen cloud absorbing specific spectral lines. But it can also be transduction, transparency. You have a glass pane, photon comes, other side, its photon shoots out. Glass pane is also about creation. You get this photon hitting the glass pane, then bouncing back, but it delivers a certain impulse. That impulse travels to the glass, and on the other side of the glass, it creates a new photon. That's creation as well. So since both the emitting chapter, Flight of the Photon part 1, and Flight of the Photon part 3, the receiving chapter, address the creation of photons, I have to shortcut those two, I have to cross-check them to see is everything alright. So I have to do a few checkups about these two. That's why I start with the easy part, the photon in flight, from the moment that it leaves the atmosphere and to the moment where it enters the next atmosphere. That's what Flight of the Photon part 2 out of 3 addresses. Here you go. This thing you can download from my website. I don't have a PDF there, but you can download the text, you can copy clip it. If you like a better resolution, mail me, and I will send this paper right to you, and you get a better resolution. Flight of the Photon part 2 out of 3, the flight of the photon itself. First some basic stuff, what a photon looks like, what a quark looks like, what a graphon looks like, a few things about bonds. And then immediately after you'll find these 6 pages showing you 6 times 6 spectral lines, all the ranges, all the series, Lyman series, Balmer series, Passion, you name them, Brackett, Punt, Humphreys, all 6 of them. And these are not just the data, the mainstream data now. Mainstream data, frequency, wavelength, and mainstream energy, they're common knowledge. But in addition, there's now the star drive energy, which is another energy component, and the forward motion of the photon. That's another energy component. Photon has in flight has 3 energy components, but on arrival we only measure one of them, one of those 3. So that's why now we have all 3 instead of just one component. In addition, you have the core-to-core distance, which is new as well. This is exclusive. You won't find this anywhere else in the world. Only VEDODER R&D gives you this kind of detail about the photon. The whole core-to-core distances. And I can calculate way more things, centripetal forces, you name it, but friction, whatever goes on. But this is just a short paper telling you a few things about the photon, not everything. I can do that, but then the paper will get very long. So you get those photons, and then of course you want to know, how do I get those core-to-core distances? How do I get that information? Did I just make it up? Well, of course not. I don't just make things up. I'm a pro. I don't do that shit. So here is an explanation of how I get to the conclusion. You get that photon. It has 3 energy components. One moving forward, and then it's the energy stored within that body, within that spinning body. There's energy stored, and that energy can be split up into 2 components as well. That's basic physics. Is how you calculate the energy stored within 2 hollow balls who are partly entwined. This is it sounds complex, but it isn't. It's very simple. You find all the equations and calculations right here. Of course, not for every spectral line, but one example you'll find here. What is important, what I'm trying to explain in this paper, is what happens when a photon, on arrival when a photon hits an object. Why do we measure a certain amount of energy, and why is that only part of the total energy? And same for a photon leaving the atmosphere. Why does it absorb a certain energy? Why do you need energy to get out of there? And what happens is a photon it's a very solid object. It's chemically bonded to gravitons. Solid object. It travels light years through space without, well, maybe a little redshift. That's a bit wear and tear. It opens up a bit, redshift. But it won't just break apart when hitting, say, a hydrogen cloud. It just doesn't dissolve into nothing. It's nonsense. It's a strong object. It just surrenders part of its energy. And here it says how it does that. It says you have your forward motion, you have your spinning motion. When it's in open space, the polarization is circular. Circular polarization, it like this. It goes through space, it melts through space like a bullet would. It has a very straight aim. But the moment it hits the atmosphere, the force fields, the force lines change. Therefore, it flips. And when it flips, it moves into a circular polarization instead of a linear polarization. So it goes from circular to linear. And when it does so, of course, it becomes less stable. But at the same time, it slows down as well. That's what this says. This paper in detail. Circular polarization through space, two vectors, one pushing the photon ahead, like this. This is the speed of light, maximum speed of light. The ether propels at the speed of light. That's the top speed. But at the same time, a vector from the side can make it spin. So it can move through space at the speed of light and still spin, which means the combined speed of this thing is above the speed of light. Now, when it flips, the same vector that moves it forward is responsible for making it spin, because those vectors will overlap. Now, you'll find it in our paper as well. You see right here. You see how the vectors are different. When circular polarized or linear polarized, the vector overlap. So this means in the fact that the fastest object of these two is this one, right? So this is now the speed of light, which means the center of it will slow down. And that difference in velocity creates that difference in energy, the mainstream energy we measure. That's what it's all about. And when knowing this, we can calculate the core distance of each photon, because I know the mass of the average graviton. That means we can calculate the core distance of the photons. You will find that information here as well within the paper. Then you have the 14 micron mark. This little graph. It isn't mine though, but I took it from the internet. Oh, that's not a problem. And it shows you that when doing so, when you have the 40 micron mark, when you take it as a point where a photon breaks up, the surface spectral lines of hydrogen, they range from the ultraviolet catastrophe to the infrared catastrophe. You know that at 12.4 micron is the longest wavelength of each photon within that hydrogen spectrum. You know, shortly after that 12.4, there must be a point where it breaks up, and at 14U we see a anomaly, and therefore I concluded 14U is the point where it breaks up. It proved to be right as well. I mean, gosh, since you have the breakup point, and you can calculate the heart-to-heart distance from that breakup point, you know the diameter of each photon. You know, heart-to-heart equals the diameter, you know this. So when you have the diameter of that photon, of that graviton, you can calculate all those energies, those other energy components. And in total, I had four different ways which tell me that the diameter of a graviton is indeed 1 angstrom. First of all, I started out with making a few estimates. You have to make a few estimates in advance to know where you have to aim for. I made 2 estimates using carbon and iron. I used the density of diamond, and diamond is carbon compressed. I know the mass of one carbon atom, 12U, and I know the density of diamond, 3.5 grams per centimeter. So I know what the masses of so I know how many of these fit in a cubic centimeter, how many carbon atoms fit in 1 cubic centimeter. When you have that, you can calculate, because I know how many gravitons fit in one of those carbon atoms. This is a triangular pyramid like these two. When you know this, how many gravitons fit in one carbon atom, you can calculate the size, roughly the size of a graviton, the volume of it, and well, it ended up with having a diameter of, say, about half an angstrom. Did the same thing for iron. IBM told us that iron is about 1 nanometer in size, an iron atom. Now, since I know how it looks in detail, I can 1, 2, 3, 4 those pyramids, know how many gravitons fit in one pyramid lengthwise, so which gave me something above 1 angstrom. In effect, you should end up around the 1 angstrom mark for the diameter of a graviton. And calculating it, I indeed came up with 1 angstrom. Using it, I used the 14 micron mark, you can do that. Then calculated it and came up with the 14, with 1 angstrom for a graviton. Now, in addition, and this is a beauty, so I determined using 3 ways. I determined the size of the graviton being about 1 angstrom. I calculated it being 1 of the size is 1 angstrom, half the diameter is the radius, which is 0.053. That's my calculation based upon the 40 micron mark. Calculation. And the fun part is, later on I discovered that Niels Bohr himself, no one other than Niels Bohr, determined that the smallest radius possible for any electron is also 0.053 nanometers. Which means both me and Niels Bohr have the same outcome when it comes to the smallest possible radius of an electron. And that's interesting. That's the fourth, and this, of course, the sherry. This is wonderful. This is the icing on the cake. If Niels Bohr agrees with you, guys, Niels Bohr. So yeah, that's wonderful. And of course, knowing this, there is no need for a Higgs particle. It's very funny. I mean, you can reverse calculate this. I've calculated this, and you can reverse calculate the mass. You can establish the mass of a single graviton using that spectral line as well by reverse calculating. When you do so, you can find it in the paper as well. When you do so, you will notice that a graviton weighs about 1/6 of a U. The graviton has the right size, the right shape, and the right mass to be 1/6 of a nucleon. There you go, nucleon made out of 6 gravitons. So, no need for a Higgs particle. I will challenge everybody to come up with a good explanation for that Higgs particle and compare it to my explanation. See what happens. Really, it's nonsense. You don't need that kind of stuff. You don't need a particle to give something mass, and you don't need a particle to give something volume or charge. It's really ridiculous how often scientists blame a particle for phenomena and then think they're good about it. Something. It's nonsense. You can't just blame particles for phenomena and then be done with it. Nonsense. It's way too easy. It's way too easy. Now, if you want real detail about the universe, real detail, which you can try to dispute it, but it's mathematics. And you can't dispute mathematics. 1 and 1 is 2. So that's all the things. You'll find these things in my paper. And of course, yeah, I say have a nice day. This is it for now. Whenever those other papers, Flight to Photon, are complete, I will upload them as well, and so forth. Only thing I don't get until now is magnetism. I have to figure out how that works. Everything else is already been deciphered and stuff. Only have to put it on paper and then upload it. So this year you'll find everything about the universe there is to know about quantum physics, about the theory of everything, ranging from the Big Bang to the Big Rip. You'll find everything this year on the internet. Have a nice day. Bye.